Welcome back to The Explainer. Today we're cutting straight through the hype to demystify how a computer actually goes about learning. We hear the term machine learning literally everywhere these days. But when you strip away all the buzzwords, what is actually happening under the hood? Well, today we're focusing on the absolute bedrock of this field, defining a learning problem. We're going to explore the formalization of learning as a very precise combination of a task, a performance measure, and source experience.
So think about this. How do you actually program a computer to learn? This is the core ambiguity we have to solve. Because, you see, humans learn organically. We often just observe the world around us. But machines? Machines need a mathematically well-posed problem. I mean, if I want to teach you to recognize a cup, I can just point to a few cups on a table, right? But a computer doesn't have our prior knowledge. It doesn't have our intuitive context. So we have to explicitly translate our human goal into a rigorous mathematical framework.
Here is our roadmap for today. First, what is machine learning? Second, the well-posed learning problem. Third, defining the task. Fourth, measuring performance. Fifth, learning from experience. And finally, the complete learning framework.
All right, let's jump right into part one. What is machine learning? Moving beyond the colloquial.
To actually build a learning program, we literally can't just command it to get smarter. It doesn't work like that. We have to be 100% explicit about the data, the process, and the evaluation. Take a database system, for example. If it just allows users to update data entries, it is technically improving its performance in answering queries based on experience. Now, we aren't really worried about whether this fits our everyday English definition of the word learning. Instead, we adopt a strictly technical definition for the class of programs that improve through experience. We need to define precisely a class of problems that a machine can actually compute.
That brings us to section 2. The well-posed learning problem, specifically Tom Mitchell's foundational framework.
So the crucial point here is this triad: task, performance, and experience. We're going to refer to these as T, P, and E throughout this explainer. According to Mitchell, a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T, as measured by P, improves with experience E. Okay, I know that sounds like a bit of a tongue twister, but it is beautifully elegant when you really look at it. You absolutely cannot have machine learning without all three of these pillars clearly defined.
To put this into perspective, let's look directly at Mitchell's original text. You can see exactly how he applies this framework to a classic checkers playing program. In order to design a program to learn checkers, the task, or T, is simply playing the game. The performance measure, P, is the percentage of games won against opponents, and the training experience, E, well, that's playing practice games against itself. Suddenly, learning to play checkers isn't some vague concept anymore, is it? It becomes a totally measurable loop.
This T, P, and E mold is like a universal puzzle piece. It brilliantly illustrates how vastly different problems fit the exact same structure. We just discussed checkers, but flip that to handwriting recognition. The task T totally changes to recognizing and classifying handwritten words within images. The performance P becomes the percent of words correctly classified. And the experience E? That's a database of handwritten words with given classifications. It's a completely different domain, but it uses the exact same framework.
Moving on to section 3, defining the task, going from concepts to statistical frameworks.
Math is simply the language we use to express a task to a computer. In statistics, every single task needs inputs, desired outputs, and a function bridging them. Our inputs are the domain set. We denote that as X. These are the objects we actually want to classify. Our possible answers are the label set, or Y. And the real magic happening in the middle is the predictor function. You'll often hear this called a hypothesis, or H, and it maps an input from X to an output in Y.
Let's use a fun real-world example: tasting papayas. Let's say our task is deciding if a papaya is tasty before we actually buy it. Our domain set, X, is the set of all papayas. Our label set, Y, is binary. It's either tasty or not tasty. Our predictor function, H, is the rule our learner will employ to predict the label of future papayas in the farmer's market based on features like, color or softness. The task, ultimately, is simply finding that optimal function, H.
All right, section 4, measuring performance. How do we actually measure success?
In statistical learning, we contrast the error rate on our specific training sample with the actual true error rate out in the real world. This is a massive distinction. It's absolutely crucial. We want our program to succeed out in the wild, not just memorize the specific data it's already seen.
Let's break this down a bit more. The true error is the probability that our hypothesis will misclassify a single randomly drawn instance from the entire unknown distribution of the world, which we denote as D. But here's the catch. We can't possibly know the true error of the entire universe of papayas or checkers games or handwritten letters. We just can't. So we have to rely on empirical risk. Empirical risk is simply the fraction of our specific training sample, denoted as S, that the hypothesis misclassifies. Minimizing this empirical risk on our known data is our primary computable performance measure.
Which brings us to Section 5, Learning from Experience. This is the fuel for the learning process.
I absolutely love this quote from Shalev Schwartz and Ben David because it perfectly captures the essence of experience in machine learning. They say the training set S is a window through which the learner gets partial information about the distribution D over the world. Think about that. Our experience is just a limited sample. It's a tiny window representing a much broader, completely unknown probability distribution. The machine doesn't actually know the world, it only knows the window you give it.
So, in formal terms, experience is a finite sequence of feature, vector, and label pairs, just like our papayas and their tastiness labels, or images of highways mapped to steering commands. These instances are generated by that completely unknown probability distribution D. Therefore, it makes sense that the larger the training sample, the wider that window gets. A larger window is much more likely to accurately reflect the true distribution of the real world, and that directly improves our performance measure on the given task.
Finally, Section 6, the Complete Learning Framework. Let's bring the whole shebang together.
Using T, P, and E acts as the ultimate bridge. It transforms messy, real-world ambiguities into a precise language that a machine can easily execute. Here's the flow. We start with a vague goal. Then we define the domain and labels to create our task. Next, we feed the system a training experience, which is drawn from an unknown real-world distribution. And finally, we evaluate our predictor function using a performance measure like empirical risk. We do this hoping that by minimizing errors in our tiny window of experience, we're actually minimizing errors out there in the real world.
So what does this all mean for you? As you look at the tech challenges around you today, ask yourself how you might break them down into this exact framework. Whether it's predicting stock prices, driving an autonomous vehicle, or even just filtering spam out of your email inbox, how would you define the task, calculate the performance, and source the experience? Finding a truly computable solution always starts with defining a well-posed learning problem. Thanks for joining me on this explainer, and keep looking for the T, P, and E in the algorithms all around you.